Today we're going to talk about springs, about pendulums, and about simple harmonic oscillators, one of the key topics in 801. If I have a spring, and this is the relaxed length of the string, spring, I call that x equals 0, and I extend the string, the spring with a P, then there is a force that wants to drive this spring back to equilibrium. And it is an experimental fact that many springs, we call them ideal springs, for many springs this force is proportional to the displacement x. So if this is x, if you make x 3 times larger, that restoring force is 3 times larger. This is a one-dimensional problem, so to avoid the vector notation, we can simply say that the force, therefore, is minus a certain constant, which we call the spring constant. This is called the spring constant, and the spring constant has units newtons per meter. So the minus sign takes care of the direction. When x is positive, then the force is in the negative direction. When f is negative, the force is in the positive direction. It is a restoring force. Whenever this linear relation between f and x holds, that is referred to as Hooke's law. How can we measure the spring constant? That's actually not too difficult. I can use gravity. Here is the spring in its relaxed situation. I hang on the spring a mass m, and I make use of the fact that gravity now exerts a force on the spring, and when you have your new equilibrium, this is the new equilibrium position, then the spring force, of course, must be exactly the same as mg. There's no acceleration when the thing is at rest. And so I could now make a plot whereby I could have here x, and I could have here this force F, which I know because I know the masses. I can change the masses. I can go through a whole lot of them. And you will see data points which scatter around a straight line. And the spring constant follows then, if you call this delta F, and you call this delta X, then the spring constant K is delta F divided by delta X. So you can even measure it. You don't have to start necessarily at this point where the spring is relaxed. You could already start when the spring is already under tension. That is not a problem. You'll be surprised how many springs really behave very nicely according to Hooke's law. I have one here. That's not a very expensive spring. You see it here. And there is here a holder onto it, so it's already a little bit under stress. That doesn't make any difference. These marks here are 13 centimeters apart, and every time that I put 1 kilogram on, you will see that it goes down by roughly 13 centimeters. It goes down to this mark. I put another kilogram on, it goes down to this mark. I put another kilogram on, and it goes back to this mark, all the way down. And if I take them all off, so what I've done is I effectively went along this curve, and if I take them off, if it is an ideal spring, then it goes back to its original length, and which it does. That's a requirement, of course, for an ideal spring if it behaves according to Hooke's law. Now, I can, of course, overdo things. I can take a spring like this one and stretch it to the point that it no longer behaves like Hooke's law. I can damage it. I can do permanent deformation. Look, that's easy. For sure, Hooke's law is no longer acting. Look how much longer this spring is than it was before. So there comes, of course, a limit how far you can go before you permanently deform the spring. What I have done now with that spring, probably in the beginning, I went up along this straight line, and then something like this must have happened. I got a huge extension. My force did not increase very much. And then when I relaxed, when I took my force off, the spring was longer at the end than it was at the beginning. So I have a net extension which will always be there. And that's not very nice, of course, to do that to a spring. So Hooke's law holds only within certain limitations. You have to obey a certain amount of discipline. There are ways that you can also measure the spring constant in a dynamic way, which is actually very interesting. I have here a spring, and this spring, this is x equals 0, and I attach now to the spring a mass, m. This has to be on a frictionless surface, and you will see when I extend it over a distance x that you get your force, your spring force, that drives it back. We have, of course, gravity, mg, and we have the normal force from the surface. So there is, in the y direction, there is no acceleration, so I don't have to worry about the forces in the y direction at all. If I let this thing oscillate, I release it, it will start to oscillate about this point, back and forth. Then, as I will show you now, you will find that the period of oscillation, the time for one whole oscillation, is 2 pi times the square root of the mass m divided by the spring constant k. I will derive that. You will see that shortly. In other words, if you measured the period and you knew the mass, then you can calculate k. Alternatively, if you knew k and you measure the period, you can calculate the mass, even in the absence of gravity. I don't use gravity here. So a spring always allows you to measure a mass, even in the absence of gravity. The period that you see, the time that it takes for this object to oscillate